Welcome to Visual Algebra Lecture 5.7, Transitive Actions. A group action, or G-set, is transitive if its action graph is connected. If we fix a group and generating set, i.e. a Cayley graph, a natural question to ask is, how can we classify all connected action graphs? The action of G on the cosets of a subgroup is an example, which is constructed by collapsing the Cayley graph by the right cosets of G. It turns out that every connected action graph arises in this manner. Said differently, every transitive G set is isomorphic to the quotient of G by one of its subgroups. Yes, we can take the quotient of G by any subgroup H, normal or not, though the resulting G set is a group if and only if H is normal. This leads to a Galois correspondence between conjugacy classes of subgroups and G sets, or action graphs, and we'll see some beautiful visuals that illustrate this. We'll conclude with a few examples of theorems involving subgroups of a certain index being normal, where the proof begins as let G act on the set of cosets of H by multiplication. And we'll discuss what this really means. This lecture is imperative for anyone who wants to really understand group actions, and I think that even the expert will find a few surprises in here. So let's get started. Let's start with a very natural question. Given a group G, what are its possible G sets? Here's an example that really illustrates what I'm getting at. Here are 5 graphs, and I want to ask which of the following can arise as an orbit of an action by the group D4. Now we've seen this first one, that's been in our writing example throughout this chapter, and in the last lecture we saw this one as well. What about the other 3? Just because we haven't seen them, does that mean that they're not possible? In general, I would like to be able to classify and understand what can arise as an action graph. And to do that, we only really need to consider the connected ones. We need some definitions. An action phi of a group G on a set S, and the corresponding G set, which is S, is transitive if it has only one orbit. In other words, the action graph is connected. It is free if the stabilizer of every element is the identity. Think of this as the action graph is completely uncollapsed. There are no non-trivial loops from anywhere. And it is faithful if the kernel is trivial. In terms of our group switchboard analogy, I think of this as there are no broken buttons except for the identity. We'll examine these last 2 in the lecture after this. But this lecture is on transitive actions. And in this language, our question above becomes classify all transitive G actions for a fixed group G, or transitive G sets. Let's say that 2 G actions are isomorphic if the corresponding G sets are isomorphic. Recall from the previous lecture that we defined G-set isomorphism, which is a stronger condition than action equivalence. In particular, G-sets are isomorphic when the actions are equivalent and the isomorphism between the groups is the identity map. So it's sometimes helpful to not just talk about the G-sets being isomorphic, but the actual actions be isomorphic, because then I can say things like the following. Every transitive G action is isomorphic to G acting on a set of cosets by multiplication. This is something we saw a few lectures ago, and a connected action graph like this is a Cayley graph collapsed by the right cosets of some subgroup. In this case, it's the right cosets of the subgroup H generated by F. So the reason why I introduce this language is because without it, and I want to talk about G-set isomorphism, I really have to say that the set S is isomorphic to the set of right cosets of H of G. And I like being able to speak about the action when I speak about isomorphism. So let's go back down here and just recall what we mean by collapsing by cosets. So I get questions about that a lot, and I just want to do an example for you. So here is is H. And here is HR cubed. These are the two right cosets that are also left cosets. Now let's draw the other right coset. So HR, I'll draw that up here, is what you get by taking H and then doing R. So this node and that node. Let's color that red. And then H, let's see, so HR squared is H plus, then R squared here and R squared here. Let's just pick a different color. What have I not used yet? How about green? And we'll do those. And then, so let's write these. So this is HR squared, and I'll also do HR to the fourth and HR to the fifth. And I'll use different colors for these. Let's say, let's use purple for one of these. That's this one. And we'll use orange for the other one. That's this one. So these are the right cosets. And when I say collapse by the right cosets, I mean is just like we do in the quotient process. That is, we preserve the edges. So from this blue coset to this red coset, we can follow the red edge from here or the red edge from here. So that's this red edge here. From this red, actually, let me do this first. Let's draw in these cosets so you can color code them like I've done over here. So the orange one is RH the fifth, and then I'm missing a color. That's the purple one, is this one. So the only path from the red coset to the green coset, so we can do R this way or R that way. So we put an edge there. And then from the green coset to this blue coset, we can go R that way or R that way, and so forth. So we cannot collapse by the left coset. Remember, the left cosets are these identical motifs. If we try to collapse by those cosets, what we'll get is, so let's just write it out. We get H, R squared H, R cubed H, R to the fourth H, and R to the fifth H. And if we collapse by the left cosets, then we just get a graph like this. Because again, those are these things here, and that's not the Cayley graph of a group at all, because there are these are double-sided edges, so there's two outgoing edges from each node. So the big idea, we can only collapse by the left cosets if the subgroup is normal, otherwise it's not even well defined, but we can always collapse by the right cosets, and whether the subgroup is normal or not, we get a transitive G set, and the idea is every transitive G set has this structure. So every transitive G set is isomorphic to some quotient. I'm going to call this the quotient of G by H. And yes, we can take the quotient of G by a non-normal subgroup. We just don't get a group. We get a G set. Here is the subgroup lattice of D4, or at least I should say the subgroup diagram, because I've collapsed by the conjugacy classes. Notice that there are two conjugate subgroups right here. This contains F and also R squared F. And this conjugacy class over here contains RF and R subgroup generated by R cubed F. And there's a bijection between the conjugacy classes of the subgroups of D4 and the D4 sets, so the transitive D4 sets. So if we fix a Cayley graph here, this is all possible results of when we collapse by the right cosets of a subgroup. Notice that the normal subgroups over here are the ones on the central axis and the index 2 ones, and over here, these are all Cayley graphs. Now, some have a few extra edges, like we don't need these red edges here, and the red and blue edge correspond to the same thing, but if you disregard that, these are all Cayley graphs, and these two are not, because they come from collapsing or taking the quotient by non-normal subgroups. Now, this is something we have to prove. Well, several things. First of all, that any time we have a transitive G set, it's isomorphic to the quotient by something, but also we have to prove that if we have two conjugate subgroups like this, and you take the quotient by them, then, in other words, we let G act on the cosets of them, same thing, then we get the same or isomorphic G sets. Here's that same statement that we had a few slides ago, that every transitive G action is isomorphic to G acting on a set of cosets by multiplication. We're finally going to prove it. Here's the basic idea. I say proof sketch, but I'll probably just do the whole thing. So to show that these actions are isomorphic, we have to show that they are equivalent, and then the isomorphism is the identity. So we first need a map that sends a set element over here to a coset over here. So let's fix an element S in our set. We're going to just denote this by like some abstract hexagon like this. So this is S. And that's going to be like our home state. So everything else in the orbit is S dot something else. So let's take S dot phi of X. And where are we going to map that to? Which coset? We don't have much choice. How about just HX, or I should say that H is the stabilizer of S. So over here we have a coset H. And what we have to show is that this bijection commutes with the group action. So that is, we start S dot over here with S dot phi of X, and if we apply sigma and then press the G button, that better be the same as pressing the G button and then applying sigma. Remember, this is the same button because iota is an isomorphism. That's why we have isomorphic G sets instead of just equivalent actions. Okay, so how do we do this? We have to show that this map is well-defined and is a bijection. So let's show that it's well-defined. So normally I say that we have to show something's well-defined if we have cosets in the domain, and we don't here, but we have multiple ways that we can express an element, and our definition depends on a specific choice. So we have to show that the map does not. So if this is S dot phi of X, that means that there is some path from S to this element, which is labeled by X. So if you press the X button from here, you get here. And suppose that there is another path, let's say Y, that gets there as well. So suppose that S dot phi of X is S dot phi of Y. So let's write this down. Say that S dot phi of X equals S dot phi of Y. We'll see if I can fit this in the margin. Well, that implies that S dot phi of X, phi of Y inverse equals S. And then I can move this inside and write S dot phi of X Y inverse equals S. And then this just means that X Y inverse stabilizes S. So that means that X Y inverse is in H. Remember, H is the stabilizer. And that just means that H X Y inverse equals H by our boring but useful coset lemma. And then we can multiply by Y and get that this is HX equals HY. And that is why it's well defined. Okay, so what about one-to-one or injective? For this, we have to assume that we have two elements here that get mapped to the same place, mapped to the same coset. We have to show that those were the same to begin with. So suppose, and let me just emphasize that this here is actually, yeah, let me write this is sigma of S dot phi of X equals sigma of S dot phi of Y. So let me put the check mark there and erase, and then see if I can erase that. Okay, so for injective, we have to show that suppose we have two set elements that can map to the same place, we have to show that they came from that they were the same to begin with. So suppose that sigma sends s dot phi of x and s dot phi of y to the same coset, which is by definition hx equals hy. Well, we have to show that these set elements are the same. That means this. Well, each one of these implications is really an if and only if. So by definition, this equivalence of the function image means that these cosets are the same, which means I can move the y over, which means that this is in H, which means that this x, y inverse stabilizes S. And let me add these. And we, by the properties of homomorphisms, we get this, and then we end up back here, and we have just shown that these things are equivalent. So well-defined, I'm just going to say make each implication a double implication, or just reverse these things. And then finally, surjective, or onto, is straightforward. We just take any coset. That's the in the codomain. So take any hx in the set of right cosets, and well, we see an element that's we see a preimage. Sigma of s dot phi of x equals hx. So we have just shown that we have a well-defined bijection between our abstract set that G is acting on and the actual cosets. So, so what this will look like is, I haven't proven this yet, but we have to show is that this bijection commutes with the action. In other words, when you start with the set element and you press the G button and then sigma, you get the same thing as applying sigma and pressing the G button. In other words, that this diagram commutes. But it does commute because, well, let's see. We start with s dot phi of x, so this element here, and we press the G button. We s dot phi of xg, and then we apply sigma, we get hxg. Well, that's the same thing as first applying sigma to get the coset hx, and then pressing the G button to get hxg. Of course, these things commute. I'm calling this phi because it's technically a different action, but both of these are just the result of pressing the G button. Therefore, we have shown that these actions are equivalent and also isomorphic because we did this with the identity map. Now, I want to prove something that I claimed earlier when I showed you the picture of the transitive D4 sets. That is, if we have two conjugate subgroups, then the corresponding G sets of right cosets are isomorphic. In terms of actions, this means if G acts on the right cosets of two conjugate subgroups, then the corresponding actions are isomorphic. And here's an example to help you understand why this is true and how the proof is going to go. So G is the group D6, and let's let H be the subgroup generated by F. So H is the subgroup right here. This is the coset HR, and notice that the stabilizer of HR is generated by R to the fourth F. You can, well, you know it's conjugate to H, but you can also see it because it's generated by R to the fourth F. So these are the other right cosets, HR squared, HR cubed. You could just see them right down here. And what I want to convince you of is why the action of G on the right cosets of H is equivalent to the action of G on the right cosets, or equivalent isomorphic to the action of the right cosets of K. So here I have the subgroup K, and I'm going to call this K. So this is K, this is KR, this is KR squared, KR cubed, and you can see, I mean, that's what this action graph is right here. And so You see the correspondence between these cosets and those cosets. I mean, so H doesn't get mapped to K, but this node looks the same as that. And then let's do some others. So this node, HR, is paired up with that one. This node is paired up with that one. This node is paired up with that one, and so forth. I need some other colors. Let's do orange with orange. And now what have I not used? How about blue with blue here and blue here? So this is how that bijection is going to go. And let's try to write it out. Notice that we are sending H. Where are we sending H to? We're sending H not to K, but we're sending H to this coset, which I'm going to write as K R inverse. So here, notice that K is R inverse HR. So if you do R inverse, I guess we don't have the Cayley graph here, but that's what K is. You can check the relations. So I claim that we are going to send H to K R inverse. So that's, this one gets mapped to not K, but this one. And so that's going to mean that HR is going to get mapped to K R inverse R, which is K. And then similarly, H squared gets mapped to KR, and that's why we have this off by 1. HR gets mapped to K, HR squared to KR, HR cubed to KR squared, so forth. So here's another picture that's similar. So in general, if you have a G set like this and call this S, the stabilizer of S is H, and then if you apply R, the stabilizer of T is R to the 4th H, which is K. So here's that correspondence between the G sets. Here it's rotated with elements, and here you can see that actual correspondence. H gets mapped to K R inverse, HR to K, HR squared to K R, and so forth. Here's another way to think about that previous example in a commutative diagram that really shows you how the proof is going to go. So H and K are as before, and sigma is the same bijection that sends a coset in here to the coset of K in the corresponding place. So notice the off by 1. So in other words, HX is going to get sent to K R inverse X. And then when we press the G button, we multiply by G. And then when we apply sigma again, we get K R inverse XG, and notice that's the same thing as just multiplying by G. So if you start with H and then you press let's do the R button first, the R button, you get over here, and then you apply sigma, you get down here, that's K. This is the same thing as first going down to this coset and then multiplying by R to get up here. But I labeled this with F because I really want to show you not just the subgroup, but a generic coset. So I start with HR and press the F button to get you to down here, which is HR to the 5th. And then apply sigma, you get KR to the 4th. That's the same thing as first applying sigma to K and then multiplying by F to get down to KR to the 4th. So this is basically how the proof is going to go. Instead of R, we're going to have A, but we have to prove that this map sigma is a well-defined bijection, and it makes the diagram commute. So notice that this diagram almost trivially commutes. You multiply by G and then stick the A inverse here. It's the same thing as sticking the A inverse or R inverse here and multiplying by G. So why doesn't this always work? Where are we using the fact that H and K are conjugate? And the answer is that this map is not going to be well defined unless H and K are conjugate. So you can try to find this map, and you can try to prove that this thing commutes. And that is a bijection, but you got to be careful. This is not going to be well defined unless H and K are conjugate. Okay, so let's prove that. This is the map that we defined previously, and this is the commutative diagram. Let's show that this is well defined. So let's suppose that we have two cosets that are the same. So xh equals xy. And then that means, well, that's equivalent to saying that h, y, x inverse equals h. And that is equivalent to saying that y, x inverse is in h. So we just have to prove that sigma, this bijection, well, we haven't proven it's a bijection yet, this map sends these two cosets to the same place. Oh, and we are going to need the fact that K and H are conjugate by A, like this. And how are we going to use this? Well, from here, we will conclude that AK equals HA, and also that K A inverse equals A inverse H. So I don't remember if we're going to use one or both of these, but they're good to have around. So let's now prove that sigma sends these two cosets to the same place. So sigma of hx is, let's write the definition, which is right here, is K A inverse X. And now look at this, K A inverse, what do you think we have to do is somehow use that relation. So this is A inverse H X. And now what are we going to do? Well, let's use, so we have an X here, and we can write H with this expression that ends in X inverse. So that's going to help us cancel. So let's substitute in for this. So this is A inverse H Y X inverse X. Notice how the X's are going to cancel. So that's going to give us A inverse H Y. And now we have this up here. So let's box that again and write that in terms of K. So that is K A inverse Y. And look what we have. That's sigma of this coset HY. Sigma of HY. And that's exactly what we had to prove. That was this is well defined. So we didn't actually need this one at all. We needed that one. Now, a lot of times we've done the proof of well defined. We've assumed that these are true, and we've concluded these, and we just reverse those arrows to show injective. So if these are true, then this is true. And I don't see an easy way to do that here. I think we can probably make it work. But the thing is, like, these things being same, we at some point get, well, yeah, so if these are the same, we can work and get these the same, and then we can multiply by A to get this. And that's something we could probably write up if we really had to. A sequence of implications starting with this, ending with these, that we could just reverse. But I think this is the most natural way to write this. So at this point, it's almost easier to just prove injectivity directly. So let's do that. Okay, so injective. Let's suppose that sigma of hx equals sigma of hy. We want to prove that these cosets were the same to begin with. So then sigma of hx equals, well, I've erased what I had up here, which was K A inverse equals A inverse H. Remember, that was our useful thing. I think will still be useful. So first of all, by definition of this map, we get K A inverse X. And then once again, we can write this as A inverse HX. So let's hold off on that, and then let's see what sigma of HY is. So this is going to be K A inverse Y, and I think a similar trick is going to give us the result. So we just write this as A inverse HY. And so if these things are the same, then look what we have here. If we have this being equal to that, if those are equal, then that implies that HX equals HY, and injectivity is proven. Lastly, we need to do surjectivity. And so this one, we just take an element that's a right coset. So let's take, this one is straightforward, take some kx, which is some right coset of G. And we want to know what is mapped to it. And so sigma of H something equals K A inverse of that something. And what we want is we want Kx. So how do we get that? So let's do A, K goes right there. Let's put that AX right there, and that AX right there. So this is the coset that by definition is mapped to Kx. And that's bijectivity. And finally, the fact that it commutes with the action, you can just read it right off of this diagram. Multiply by G, apply sigma, sticking an A inverse is the same as sticking in an A inverse and multiplying by G. And that's the proof. Let's summarize the big ideas here, because this is really important, what we've learned. In chapter 4, I described the fundamental homomorphism theorem by saying every homomorphic image is a quotient. So that is if phi goes from G to H, and then the image of phi is isomorphic to G mod n. I could have said that as the quotient of G by any normal subgroup is a homomorphic image. And that's kind of what this is saying more generally. Every connected transitive G set is just a quotient by not a normal subgroup, but just an arbitrary subgroup. Or equivalently, every transitive G action is isomorphic to G acting on the cosets of the stabilizer. The action graph is constructed by collapsing the right cosets of the stabilizer, and conjugates of the stabilizer give the same G set, or isomorphic G sets. A few slides ago, I showed you a picture like this, but for the group D4. And since then, we have actually proven that there's a bijection between the conjugacy classes of subgroups and the transitive G sets. So I just think D6 is a little bit richer. So the index 2 subgroups are normal. Of course, the whole thing in the trivial group is, and this is the center, and this is normal as well. And here are the three conjugacy classes of non-normal subgroups. Notice that those are the action graphs that are not Cayley graphs. Everything else is a Cayley graph of a group, potentially with some redundancies in there. Earlier, I said that the correspondence between these two things, I call this the G-set post-set, is a Galois correspondence. And that basically means that it's order reversing. So the bigger things up here, when you collapse by them, lead to smaller things down here, and vice versa. These small subgroups, when you collapse, you get larger G-sets. And you can actually formalize this, like if A is contained in B over here, then when you apply this, say this is a function f, and then f of A is, I'm going to say, bigger than f of B. By this, I mean this thing is a quotient of that thing. Later in this lecture series, we're going to see another Galois correspondence we get to field theory and Galois theory at the very end, chapters 10 and 11. This is the most famous example, is actually where the name Galois correspondence comes from. It has something to do with, take a polynomial, and you look at what field of numbers does it completely factor, and all the subfields. There's this correspondence between these subfields and these subgroups of something called the Galois group, which is basically the automorphisms of those fields. So it's a really cool subject, and I hope you stick around and make it that far. I want to finish this lecture by saying a few words about things that we can prove by letting groups act on cosets. It's a useful technique for establishing seemingly unrelated results. Several of these involve showing that subgroups of small index, for what I'll explain shortly, are normal. We've already seen that subgroups of index 2 are normal. And of course, there are non-normal index 3 subgroups, like the order 2 subgroups in D3. But the following gives a sufficient condition for when an index 3 subgroup is normal. It says that if G has no subgroup of index 2, then any subgroup of index 3 is normal. When you see this for the first time, it's not in any way clear how to approach it. Some proofs, many that we've seen, are, I call them follow your nose. You just write down the only thing you can write down and it leads you there. This one is not like that. So let's let H be a subgroup of G with index 3. And we're assuming that there's no subgroup of index 2. And let G act on the cosets of H by multiplication. That means that we get a homomorphism from G to S3. And this is a non-trivial homomorphism because we know that we can get from any coset to any other coset. So this is non-trivial. Remember, because if we have Hx and we have Hy, there is some path, something we can multiply this by to get that, namely just x inverse y. So let's let K be the kernel of this homomorphism. And though we don't need it for the proof, you may recall when we looked at examples of group actions, that K is the largest normal subgroup of G contained in H. Here's what that really looks like. So here's G, here's H. This has index 3. And then H is conjugate to, maybe nothing else, but in general, could be conjugate to other things. And then K is I call it the base of the conjugacy fan. So if you take everything conjugate to it and you intersect them, you get a subgroup here, and we proved earlier that that was normal. Now, remember that there might be subgroups that are intermediate in here. I'm not saying that there's nothing here, but if you intersect these, you will get something that I called the base of the conjugate fan, which is normal, and that will always be the kernel of this action. Now, by the fundamental homomorphism theorem, we know that G mod K is isomorphic to the image of phi, and that is a subgroup of S3. So in other words, if we take this quotient, G mod K by the correspondence theorem, this subgroup lattice has to have the same structure as a subgroup lattice of a subgroup of S3. And there's not that many subgroups of S3. We also know that the kernel is not equal to G because this is a non-trivial homomorphism. Thus, there are 3 cases for this quotient. G mod the kernel is isomorphic to S3, to C3, or to C2. Visually, that means that we have one of the following. by the correspondence theorem. Now, what can we rule out? Well, we know that in the original subgroup lattice, we had G and H. We know that this was index 3 subgroup, so that immediately rules this out. So that's not possible. So we have one of these two things. But we also have the assumption that G has no subgroup of index 2. And look at this. If this is the case, then that would imply that by the correspondence theorem that N is an index 2 subgroup. And we know that that is not possible. So this one is ruled out. So we have to have this. So we know that in general, we know that K is contained in H, and G mod K is C3. So here's what we have. We have K down here, and K is index 3 in G. So by Lagrange's theorem, this has to have index 1, which means that H and K have to be equal. So we have thus concluded that the kernel of phi, which we called K, has to be equal to H, and we know that kernels are always normal. And that's what we had to prove. We showed that if there was no subgroup of index 2, then any subgroup H of index 3 was normal because it's the kernel of this homomorphism. So you may be wondering, why am I showing you this exercise in this lecture on transitive actions? Well, it's because when I took algebra, I thought it was kind of strange that I'd see these exercises and the solution would start out with let G act on the cosets of H by multiplication, and then we do something and we get that H is normal. And here's what's really going on. Here's a different way to say that. We could say, given a subgroup H, consider the G set, which is just the quotient of G by H. In other words, given H, take the quotient. And that comes from an action. And in that action, H is the kernel. So it's just a little different way to think about where that comes from. And for me, it makes it a little bit more motivated. And I want to finish this slide with an exercise I encourage you to try. So if G is simple, that means that it has no normal subgroups other than G and the trivial subgroup. Well, we know it has no index 2 subgroups. Those are always normal. From this exercise, we know that it cannot have any index 3 subgroups because those would be normal. But I claim that it also cannot have any index 4 subgroups. So then it has no index 4 subgroups as well. And the solution of this is similar. You just have to do the same thing, but now you get something isomorphic to S4, and there's more cases that you have to check. But if you go through them, and it's really hard to do without the subgroup lattices, but if you have the lattices, you can do them one by one and make sure that none of these things work out. So I encourage you to try that. It's a really good exercise. Our last result is similar in spirit to the previous one. It involves a subgroup of small index being normal. This time, H has index P, which is the smallest prime dividing the order of the group. The proof of this will start out just like the last one. Let G act on the cosets of H by multiplication. And so equivalently, you could say, or consider the G set defined by collapsing by H. So this defines a homomorphism from G to the permutations of the cosets. So this is a p element set because that is the index. That's the number of cosets. So this is a homomorphism to SP. So here's what we have. We have G. We have H, which has index P. And in general, H might be conjugate to a few things. This might be X, H, X inverse, etc. And the kernel K is a subgroup of H. And we're going to show that K equals H, which means that H is normal because kernels are normal. So here's what we know. If we take the quotient by K, so let's take I'll let you write this out formally, but I'll just draw a picture and explain it. So by the correspondence theorem, we take the quotient by K, and H mod K has index P and G mod K. And let's say that K has index Q. We want to show that Q is equal to 1. Well, G mod K is a subgroup of SP. So what that means is this entire quotient divides P factorial, or this entire index divides P factorial. So in other words, PQ divides P times P minus 1 times P minus 2 all the way up to 2 times 1. And P is the smallest prime dividing the order of G. So this tells us that Q divides, so this here is P minus 1 factorial. So Q divides P minus 1 factorial. But also, Q divides the size of the group because, Q divides the index. H has index Q in here, then Q has to divide the size of the group. But P is the smallest prime dividing the size of the group. So Q is a divisor of P minus 1 factorial, but none of these primes divide the size of the group. So that must mean that Q is equal to 1. And I'm not going to write that down. I've explained it. Which means that H is equal to K. And we know that kernels are normal. And that is that. So isn't that neat? So that brings us to the end of this video. But the next video is on simply transitive actions. So transitive means that the action graph is connected. Simply transitive means that the action is also free, which means that the stabilizer of every element is trivial. And what that means is the action graph is like as uncollapsed as possible. And we know that Cayley graphs are examples of uncollapsed action graphs. And we'll show in the next lecture that every simply transitive action is a Cayley graph, or is isomorphic to a G set, which is a group. And then we'll see a whole bunch of examples of these things arising, especially from tilings of polygons, polytopes, of the plane, and also of hyperbolic space. So there's a lot of really fun pictures coming up in the next lecture. You're not going to want to miss it. I'll see you then.